West Africa before they get to Southern Africa, bring them into our country, and then we get the dusty and dry conditions that we see in the dry season. So in the dry season, the Northern African high pressure centers are actually the ones that dictate the weather that we get here. In the rainy season, however, we get the Southern Hemisphere high pressures, that's St. Helena, taking precedence. And so you get higher pressures building over St. Helena. And so winds will move from that high pressure area to feed the lower pressures that are always around the equator. So most of the time around the equator, you get lower pressures. So that's what we call the equatorial trough. That's the low pressure extending along the equator. As a result, like I said, higher pressures in the northern hemisphere will bring dry conditions into those areas. If you get higher pressures over the ocean, they will also bring moist conditions into those areas. So depending on the pressure system, which is active at that point, will tell you what kind of weather you should expect around the equator where we find ourselves as Ghana. So we are really interested in these high pressure centers, both the Azores, the St. Helena, and then the Libyan High or the Arabian Ridge. That's the one from UAE coming into the continent. All these play a very critical role in the weather that we get here. And so, like I was saying earlier, if the Azores or St. Helena is around 1024, like we're seeing on this map, and then the pressure gradient is not too high. For instance, if we are seeing close to the coast of Ghana, there's just one isobar covering the entire coast, Gulf of Guinea. The 1010 is just covering the whole area. What it means is that pressure gradient within that area is quite low, and so winds will also be lower for that area. In that instance, you're not expecting so much moisture to be thrown in from St. Helena into the country, because Azores is even higher, and there's a high pressure created just around Northern Africa. And so around this time, the North African high pressure centers will be having more impact on the weather that we will get in Ghana. And this was taken in February, which is when we get the dry conditions. So we are getting the ridge extending from Northern Africa towards the south. And so they bring the dry, dusty weather conditions from there to affect us in the country. But in the rainy season, we get very high pressures building up over the ocean. And so lower pressures are built in the country. And these attract winds from the ocean as a result of the higher pressures, and then they feed into the country. But another thing that we should also know is that the higher the pressure in St. Helena could also tell us which areas we should be expecting rainfall. For instance, if we are getting St. Helena to be around 1025 hectopascal, that's a central closing isobar of St. Helena is 1025 hectopascal. And then Azores is quite weaker. So we assume that St. Helena will now be dictating the weather for the country. Because it is not too strong, the strength of the high pressure is not too high, you would expect that moisture will be limited to the southern parts of the country, because the winds will be stronger over the ocean, but when they get to the coast of Ghana, they will reduce before they get to the northern portions. And so the moisture will be depleted around the southern parts before they get to the northern portions. So this will favor southern Ghana more than northern Ghana. But when they increase around 1030, 1035, 1040, you get very high winds blowing all the way from coastal Ghana, but they become lower or lesser in the northern portions of the country. So when it's very high over St. Helena, northern Ghana benefits more than southern Ghana. And when it reduces, then areas in the southern portions also benefit. So you're not just looking at the value, the ridge coming into the country, but the value also plays an important role in which areas you should be expecting weather conditions to be seen. So first, you look at the whole continental pressure systems. So that's why we have Africa and then Ghana. You are looking at how all the pressure centers are behaving, how which areas have lower pressures, which areas have higher pressures. You are interested in all these things to know how winds will actually be flowing, whether they are flowing from the ocean or from the continent, and what conditions they will be carrying along with them as they come into your country. After you're done with that, you get a global overview or a continental overview of how the winds will prevail. And then you also want to now scale into your country to see what is happening within Ghana. We all know that pressure can be varying from even within a short, a lower coverage. You can have different pressure values. And so you want to zoom into the country to know what is actually happening within the country. You cannot just use the pressure over the continent to make forecasts for individual areas within the country. It can give you an overview, a synoptic overview of how the weather will be within the country, but not specifically what will happen maybe within the Ashanti region or within the Greater Accra or anywhere in the country. For instance, this one that we are seeing, if you look on the African map, you are seeing that the 1010 is a deeper red line, which covers almost the entire country and almost everywhere in West Africa. So it means that the whole West Africa is within pressures lower than 1010. So we are getting very low pressures within West Africa. But if you come to Ghana, you are seeing that there's also a high pressure around the eastern region, which is 1009. If you look around, pressures around will be lower, 1008, 1008.5. What it means is that you're getting higher pressures there, even though generally the whole country is under lower pressures, but within the country, some areas have higher pressures. So this is what I was talking about, that you don't really use a value to determine higher pressures and lower pressures, but you look around and see if the pressures are reducing or they are increasing. That will tell you whether it's a high pressure area or a low pressure area. So in Ghana, we are seeing some spot highs within Ghana, one in the northern part of the country, one around the eastern region. And then around the transition areas, we are seeing some low pressures built there. So you have to consider all these areas before you make your forecast. Even though around eastern region, the pressure is 1009, which is lower, it will still inhibit some kind of cloud formation compared to other parts of the country where we have lower pressures. And so if you are predicting weather for Ghana, you'll be more concerned over areas where you're getting the lower pressures than areas where you're getting the higher pressures. And you also have to monitor this over time to see how that high pressure center will behave, whether it's going to reduce over time or it's still going to increase with increasing time, which will then tell you what weather you should be expecting within the area. So you don't just consider the values, you look at how they are increasing or decreasing with time, and then how they are increasing or decreasing with distance. That's areas around them as well. So in a nutshell, I just want us to just look at this video and see how pressures affect weather conditions within the country. Okay, so this was just a short illustration of how pressure actually affects the weather that we see on a daily basis. So if you're getting lower pressure areas, then we are expecting rising air motion within these areas. And so you can have the clouds forming and eventual precipitation. Areas where you're getting very high pressures would have subsidence. And so winds are rather sinking. They don't really help in cloud formation and then precipitation or convective activity is happening. And so in low pressure areas, that is areas where you are actually looking out for weather. In high pressure areas, you are just expecting some fair weather conditions to be experienced within these areas. And so when you pick a pressure chart, you are interested in low pressures, high pressures. That's one thing. Once you are done with these, then you now focus on how the high pressures are behaving. Either it's it's extending to other areas, which is the ridge. And if it's a low pressure, areas where the trough is extending to, which will also give you an indication of what weather you should expect within these areas. So those are the techniques you want to look out for when you pick a pressure chart. All right, so I'm sure you know of the National Oceanic and Atmospheric Administration, NOAA website, which gives you a lot of forecast products. The only disadvantage with the pressure there is that it only gives you pressure for West Africa. And so you're not able to see how the other pressure centers are also behaving and then the impact that they will have on the weather over your area. And so the first one, which is the pressure chart from ECMWF, the European Center for Medium Scale Weather Forecasting, will give you a global view of pressure and also the continental view of pressure. And so for a larger or a synoptic view of pressure, I would advise that you use the ECMWF, which is the first link to get pressure for other parts of the continent or the globe as a whole before you zoom into the one for West Africa as captured on the NOAA chart or the CPC model. There's also weather chart which will also give you other forecast models, but they also use either ECMWF or GFS products. And so if you have access to ECMWF and then the GFS from NOAA, you don't really need that one per se. But if you don't have access to them, you can use that one to get both from the ECMWF and then the GFS product. So these are areas where you can get some pressure charts to also analyze and make your forecasting. Now, we would want to move on to a wind chart. Wind chart will be looking at different levels in the atmosphere, from the low levels to the high levels or the top of the atmosphere. And on a wind chart, these are the things that we are actually looking out for. So whether there's a cyclonic vortex or a cyclonic flow. Cyclonic vortex is when you get the winds all converging at one point, flowing into a center. That is when a vortex is created. But when it is just in the northern hemisphere, when you're just having some anti-clockwise movement, then you are expecting a cyclonic flow within that area. When you are getting clockwise movement, then that is an anticyclonic flow. And so we are looking at the vortices, both anticyclonic vortex and cyclonic vortices, and then the flows as well, whether it is clockwise or anti-clockwise. All these things can affect the weather conditions that would happen within an area. And also, you're also going to look out for the source of the wind, whether it's a maritime wind or it's a continental wind, because where the wind is coming from will tell the kind of conditions that the winds will come with. The winds get modified based on the surface that they are tracking. That is why I said that in the Hamilton, the source of the dust we get here is not actually from Ghana, but because the winds are moving from Chad, Niger, Sudan areas, Nigeria into Ghana, they come with these dry and dusty conditions there along and deposit them into the country, leading to the dusty and dry conditions that we see around that time. So the source of the wind is really important because in the rainy season, we get the source of the wind from the ocean as a result of the intensification of the Centennial high pressure. The winds are pumped from the ocean into the country. And once they come from the ocean, they carry the moist conditions from there and bring them along into the country, which leads to warm air, leading to the cloud formation and then the precipitation that we get around that time. So it is really important to know where the wind is coming from to tell you what kind of condition that it will actually be coming with. And then the direction and the speed of the wind also plays a very critical role in forecasting. For instance, if winds flowing from the ocean are quite stronger, then the amount of moisture that they will carry will also be more. If they are weak, then they will not be able to carry lots of moisture into the country. But another thing that we should also look out for is that it depends on the level where you are looking at. For instance, if you are looking at, let's say, 700, which is seen as the mid level of the atmosphere for us here in Ghana, if the strength of the wind at 700 is weaker, you'd expect that propagation of rainstorm will also be delayed. And so it will take a longer time for a storm to move from one place to another. But when the strength is higher, it moves faster. And so within a short period of time, rain might have occurred and ceased. But when the strength is lower or you have weaker winds, you get very delayed rainstorms, and so it can stagnate for a longer time, rain for a longer period of time. So you look at the direction and speed at different levels, and these levels will all have different interpretation of how the winds will affect the direction or the speed of the wind will affect the weather over the area. We're also looking at convergence at the lower levels. And so one of the basic things you need for convection to happen or for cloud formation is convection at the lower levels. If the winds from opposite directions are meeting and then rising, that's one form of convergence. There's also another form of convergence, which is the velocity or the streamline convergence. In that case, all the winds are moving in the same direction, but then the speed is actually different. It's like you um, running, two people running. Let's assume that we are all running with the same speed. We are never going to collide if we are moving in the same direction and then with the same speed. But the moment the person in front of us decide to reduce the speed, then it means that if that speed continues while you maintain the initial speed that you had, in a matter of time, you just collide with a person. So that's what we mean by velocity convergence. The speed ahead is lower, and so as the winds behind have stronger wind speed, they will merge with the ones that are ahead of them in a time to come. And so if the winds are moving from the ocean and they are very strong over the ocean, but they get weaker maybe along the coastline, what it means is that the moist winds from the ocean will be converging just along the coastline. And so the moisture will be deposited along the coast, and this will favor coastal areas with rainfall and cloud formation. If you get the stronger winds flowing all the way along the coast into the middle portions of the country and they get weaker in the mid portions, what it means is that you're getting streamline convergence or velocity convergence in the mid portions. And so the moist winds from the ocean will be converging around the mid portions and then depositing the moisture there, helping cloud formation and then eventual precipitation. So you're interested in the direction, the directional convergence, and the velocity convergence because all these things will all play a role in the weather that you expect within an area. Also, the opposite within winds, whether the winds are actually moving apart or they are moving in different directions. This will also have an effect. So convergence will help in cloud formation and eventual precipitation, but divergence will just be stopping some of these cloud formation and then precipitation that you expect within an area. All right, and so this is the dynamics of winds in the atmosphere. We say winds move from high pressure areas to low pressure areas. And so, for instance, we are saying 1028 as a high pressure center for the first one on the top there. Let me try and use the laser or a pen to make it more visible. Okay. So, for instance, here we are seeing high pressure is building up here. What it means is that winds will be moving from this center to feed this lower pressure area. All right. So this will be a high pressure center. This will be a low pressure center. In high pressure centers, winds are moving from the center away from the center. In the low pressure area, winds are moving from outside into the low pressure area. And so, for instance, this one will get the winds flowing like this in the clockwise manner in the northern hemisphere to feed this low pressure here as a convergence. So you're getting divergence in high pressure areas and you're getting convergence in low pressure areas. So when, like I was saying earlier, if before you determine whether this an area is a high pressure or a low pressure area, you get 1028 as a high pressure center. As you move away, this is 1024, this is 1020. So the pressure is reducing as you move away. So it tells you the area is a high pressure area. If you come to the low pressure area, the center is 1012. As you move away from the center, pressure is increasing. So from 1012, you go to 1016. So it tells you the area is a low pressure area. So it's not necessarily the amount or the value of the center, but areas around will tell you whether it is a high pressure or a low pressure. And this will also detect the kind of weather or winds that we should expect. So like I said, we want to be moving from the high pressure area to feed the low pressure area. So in this instance, you look at where the high pressure is built, the area where you're getting the wind flowing from. If it is coming from the ocean, then you expect that within the low pressure area where the winds will be converging, there will be lots of moisture deposited in these areas. As a result, you'd expect loads of cloud formation within this area. But when you are seeing these high pressures over land, or let's say over a dry area or a dusty area, then what it means is that it will be carrying these conditions over those areas to deposit them into the lower pressures. And so it depends on the area where the high pressure is actually situated. If it is on the ocean, you get lots of moisture in the low pressure area. If it is on the land, you get lots of dryness coming into the low pressure area. And so in times where you get an intensification in the dust and hazy conditions that we see in the Hamilton, we get lower pressure centers building up here in the country, and then higher pressure centers building up around Chad areas. And so as the winds move from there, they are deposited into the low pressures built in the country. And so we get lots of dust in the country, which causes the reduction in visibility that we see, and then the dry, dusty conditions that we experience around that time. So that's how winds behave, the dynamics of winds, high pressures influencing the wind flow, and then inflow into low pressure center areas. And this is just telling you the directions, how you tell wind. And so, like I was saying earlier, you are not just interested in the direction of the wind, also you are interested in the speed of the wind as it comes into your area of interest. For instance, if we are looking at this place, the wind there is about 60 knots, and the direction of the wind is a southwesterly wind. And so, if you are getting these winds into the country, what it means is that very high winds from the ocean coming into the country, and so you expect lots of moisture to be thrown into the country. But if you were getting this one, for instance, this is a northerly wind with a speed of 30 knots or 15 meters per second. So what this means is that the winds are continental winds if they are coming into the country as such, and so they'll come with dry conditions into the country. And so the effect that these winds will have on the area will depend on the direction, that's where they are coming from, and then the speed will also tell you the amount of those conditions over the source areas that will be able to carry along and deposit them into your country. So you are not just interested in the winds, you are interested in the direction, the source of the wind, the speed of the wind, and the curvature as well, whether it is clockwise or anti-clockwise. This will all have influence on the weather that you would experience within an area. So that takes us to cyclonic and an anticyclonic flow. So like I was saying earlier, in a cyclonic flow, you're getting the winds moving from outside into the center. And so you're getting a convergence at the center. In an anticyclonic flow, you're getting the wind starting from the center and then moving away from the center into the outside. And so you're getting fair weather conditions. So in low pressure areas, we are getting rising air motion. Same for cyclonic areas. So if you want to look out for areas where cloud formation is possible or precipitation is likely, you are looking at lower pressure areas and then cyclonic flow areas or vortices. So there's low pressure there, which will help rising air motion. There's also a cyclonic flow there, which is the anti-clockwise in the northern hemisphere, which will all help in the rising air motion. So like the illustration you're seeing here, in a low pressure area, they're getting the winds meeting and then rising and then getting cool and then condensing as they move into the top of the atmosphere, forming the clouds. And then if all the conditions are okay, you get sinking air motion and then they come down as rainfall. And so at the lower levels, you need convergence. And these convergence also depend on other factors. If the cape is higher, you're getting a higher convective available potential energy. The strength of the wind is also higher. Then you are going to get a higher updraft. And this will help in building convective clouds, and then they will be more deeper. And so you'd have denser clouds forming in areas where the cape is higher, lower pressures at the surface, and convergence at the surface as well. These will help rising and then deep convection in these areas, leading to deep cloud buildups and then eventual precipitation coming out of them. But in the opposite one, we are seeing winds sinking. So you see them, they are coming down as such. And so you're getting fair weather conditions in anticyclonic flows or high pressure areas. So high pressure areas are actually associated with anticyclonic flows. But let me state that not every high pressure area would have anticyclonic flow. So I would advise that you don't use all anticyclonic flows, don't consider them as high pressure areas because within that area you could have pressures. Like I said earlier, high pressures are not actually determined by their value, but by areas around them. And so even though the whole area may be a cyclonic flow or vortex, you could still have some areas having higher pressures. And so these will all affect the kind of weather you would expect within these areas. And so just treat them as individual, separate areas. Don't just think that all the area covered by a cyclonic flow will be under lower pressures, or areas covered by an anticyclonic flow will be under higher pressures. So just look at the individual areas or shorter unit areas to see how the pressures are actually behaving within them before you make your projections for those areas. So for us here in Ghana, we use 95 hectopascal and 850 hectopascal as our low level winds. And then we use 700 hectopascal and 600 hectopascal as our mid-level wind, and then 200 and then 100 hectopascal as our high-level winds. This will also depend on the area. For instance, for most low-lying areas, Greater Accra and by extension most parts of the coastal sector, this is a low-lying area, and so we use even 95 will not necessarily be our low level. You can still go below that low level, about 10 meters wind, which will be very close to the surface. But if you move to somewhere like Abetifi, which is a highland or high ground area, 925 may not necessarily be the low level wind. So in that instance, you could have the low level starting from 850 hectopascal. And so it depends on the area. If it's a high area, for instance, areas in South Africa, places in South Africa use 850 hectopascal as their low level wind because that's a high ground area. But for us in Ghana, we use 925 and 850 as our low level. 700 may not necessarily be a mid level in other parts of the world. It could even be a low level wind. But for us here, we consider 700 and 600 hectopascal, even up to about 500 hectopascal as our mid level, and then 200, 100 hectopascal as our high level. So let's just assume that these are the standard pressure levels that we'll be considering. But most of the time, we look out for winds at 925, 850, 700, and 200. We use 925 and 850 to tell how deep the convergence or moisture is at the lower levels. If these cyclonic or convergence or lower, cyclonic flows are reflecting on the 700 hectopascal level, and it's telling you that the convergence is actually deeper, so from the surface to the mid levels. And if you're getting the corresponding divergence at the upper level, then these are favorable in an ideal case for cloud formation and eventual precipitation within that area. So you treat this with respect to the location where you are considering. You don't just generalize these things for a wider area. For instance, if you are making a forecast for the Ashanti region or Kumasi, and you want to use information for the whole of the region to make a forecast for just that location, which is Kumasi or KNUST, you'd end up getting the forecast right for somewhere in the Ashanti region, but then wrong for KNUST area. And so when you want to make a forecast for a local area, you'd want to consider the winds at these particular areas, not at the synoptic scale within that particular area. And this is some of the challenges that we have within Ghana as one of our forecasting challenges, because most of the models that we use actually are global models. And so they give you products on a synoptic scale. And therefore, if you make analysis of these products and then you come up with a forecast, they will rather be synoptic forecast rather than localized forecast. And so they will not reflect the conditions everywhere within the area. You get the forecast being okay for some areas and then other people also complaining. So the best thing that I would recommend if you want to forecast for a particular area is not to depend solely on the global models, but you could use some local models that will give you conditions over that particular area than just relying on global models. For instance, even if you are using the global models, there are some products that will help you better. For, for instance, if you're using the T5, for instance, it's giving you conditions over a particular area, the absence of parcel of air within that particular column of atmosphere. They'll tell you what is happening within that layer, column of air layer. And so it will not be widespread for everywhere. So if you're using this, you are getting the conditions for that particular area, not a wider coverage. And so you want to consider all these dynamics when you are making a forecast. All right, so we move to the lower levels, which is the 95 hectopascal and the 850 hectopascal level. So at these levels, we are also interested in the source of the wind, in the direction of the wind, in the speed of the wind, in convergence, whether directional or velocity convergence, and then in cyclonic flows and anticyclonic flows. These are the things that we are considering when we pick a low level wind chart. We want to know where the wind is actually blowing from. Okay, so when we're done with the low levels, we'll take just some few minutes break, and then when we come back, we'll continue with the other levels. So when we pick a low level wind, we are interested in where the wind is actually blowing from. Is it coming from the ocean? What is the speed of the wind? Will it be able to carry enough moisture as it comes into the country? How is it moving? Is there any convergence? Are we getting winds meeting from any point? Are we getting the speed reducing as it moves, leading to velocity convergence? Are we getting some anti-clockwise flows around a specific area, or we are getting clockwise flows in an area? All these will just tell you what kind of weather conditions that you should expect. If the source of the wind is from a dry source, like I said earlier, then you would expect dry conditions coming into your area. If it's from a moist source, you're expecting moist conditions into your area. Then the direction will also be limited, will also be reference to the source of the wind, because where the wind is directed from will tell you whether it is coming from a dry area or a moist area. And then the speed, like I said, will tell you the amount of those conditions, whether dry or moist, that these winds will carry as they come into your area. And then convergence. So if they are moving in opposite directions that they are meeting, at that point, you would expect that if the source of the winds are moist, you would expect some cloud formation and eventual precipitation. If the source is dusty, then you're expecting dusty conditions merging over an area, and so producing some dry and dusty conditions within these areas. And then for cyclonic flows too, like I said, those are areas where you're expecting rising air motion. And so if you're seeing cyclonic flows in an area, you would expect that level surface conditions. We've also looked at the winds at the lower levels, which is 95 and 850, what we should look out for when we get to these points. And we'll go to the mid levels and then the high levels. But I want us to take some 5 to 10 minutes break. It's sorry, I think it's almost 11, about 10:56. So we'll start again around 11:05 with the mid levels and then the high levels. Right. Sure, sure, it's okay. Yes, yes, that's fine. Sure, sure, that's fine. Okay, so there's the WAF model, weather research and forecasting model, which is a local model. So it uses the conditions over that particular area to build that kind of model. And so the products that you'll be getting from these will represent the conditions over the area better than the global ones, which will just use a synoptic scale representation. So WAF is one of the models. Unfortunately, for now, WAF at GMX is not operational. So we rely mostly on these global models. Yeah. Wow. Okay, so we'll do that. There's a way. We'll still have to rely on these global models, but there should be a way we can also fine tune some of these models to predict better for our locality. And so we'll actually look into that. I think that is tomorrow when we're looking at how we monitor and then validate some of these models to make forecasts. So we'll actually go into that and see how best we can maneuver our way around using global models because you cannot run your own model, so you have to rely on some of these models. Okay. Oh, I'm running fast there. Oh, okay. Okay, sorry about that. I'll have to mute the um, computer here so that we don't break it. But I tend to talk faster, so when I'm going fast, you can alert me so that I slow down. Yeah. But is there any other question? Okay. Sorry, we can go on. Yeah, around 11:05. Okay, no problem. All right. All right. So I will even want to pick something, so I'll be right back. Yeah, I can hear you now. Okay. Let me put it back in presentation mode. Okay, so we'll move straight to the mid levels and then the high levels. All right. So at the mid levels too, we are interested in the direction of the wind as well as the speed, and then the cyclonic and then anticyclonic flows, because we want to know how deep the cyclonic flow is. That's from the low levels to the mid levels. If they are deeper, if you're having cyclonic flow at the low level and the mid levels, then they help in sustaining cloud developments through the lower levels to the mid levels of the atmosphere. But when it's just cyclonic flow at the lower levels, you have the clouds building up at the lower levels, but they are not able to extend into the mid portions of the atmosphere. As a result, you get shallow clouds, and then they don't produce so much rainfall. So to get these kind of convective rainfall lasting for a while and producing heavy amounts of rainfall, you would need deep cyclonic flow. So from the low levels to the mid levels, cyclonic flows. If you're also getting cyclonic and then anticyclonic at the mid levels, like I said earlier, then you'd have clouds development being shattered at the mid portions of the mid portions of the atmosphere. Okay, so we are interested in the flows both at the low and the mid levels. We're also interested in the speed both at the lower and the mid levels. And we're also interested in the direction from the lower levels to the mid levels. So these are the things that we are interested in. Around this point, you can also talk about the source of the wind as well. For instance, if you are talking of 9 to 700 hectopascal. Oh, sorry, you're not so much interested in the source of the wind here because surface conditions will move surface winds into the country, and so the source will play a vital role in the conditions that you would expect in the area where the winds will be going to. But at the mid levels of the atmosphere, you are not so much interested in the source because you could have moist winds over a dusty area or a dry area. The surface could be moist, could be dry, but then the mid levels could be moist, and so it would not really have so much effect on the weather that you get in your area. So you can still use the relative humidity chart, which we will go through later, to tell how deep the moisture is from the lower levels to the mid levels. But you're not really interested whether it is coming from a dust source area or it is coming from a maritime area, because at this point you are not so much interested in this. Is not telling you what is happening at the surface. It's just the mid portions of the atmosphere. And then the high levels. High levels, I have asterisks on the wind direction and the wind speed because I'll go back and explain that. So you are still interested in the cyclonic and then anticyclonic flows here. When you have cyclonic at the lower levels, cyclonic at the mid levels, and you get anticyclonic at the upper levels or the high levels, then that's the ideal case for convection to happen, cloud formation, and these kind of rainfall that we get. If you're having cyclonic flow throughout the layers of the atmosphere, then you are looking at clouds building up all the way from the lower levels to the high levels. But these will not produce so much rainfall because, in as much as you need the updraft, you also need a corresponding downdraft, which will bring the clouds down as rain. And so, if you're getting just the updraft and you're not getting the downdraft, then obviously you may get some rainfall, but it will not be as intense as the ideal case where you're getting cyclonic, and then anticyclonic at the upper levels of the atmosphere. And so you're looking at areas where you have cyclonic flows, anticyclonic flows, and relating them to the surface and then the mid levels of the atmosphere. Let me also state that in forecasting, you don't treat any chart as a separate chart. You try to connect all the charts. So we've gone through mean sea level pressure chart. We've gone through the winds at the lower levels and then the mid levels of the atmosphere. But you'd also want to link this with the higher levels. And so what is happening at the high mid levels or the lower levels should be linked with what is happening at the higher level in order to make a prediction. because if you treat them separately and you see anticyclonic flow at the high levels of the atmosphere, you might think that it will aid cloud formation or precipitation. But if the conditions at the lower levels are not too good, then obviously it will not even get to that point where the high clouds or the high conditions will favor the precipitation or the cloud formation. And so you consider from the bottom to the top of the atmosphere all the conditions from pressure to the winds at 925, 850, 700 before you get to the high levels of the atmosphere. All right. So about the direction and then the speed of the wind at this point, this becomes relevant when you are monitoring, let's say, a rainstorm. For instance, if we have storm moving from the east towards the west, which is usually the case. In rare instances, we get systems moving from the west towards the east, and that mostly happens either from the transition into the dry season or during the dry season. That is why we get some of these things happening. This is what we expect. At the lower levels, we are getting cyclonic wind flow, which is aiding in cloud formation and cloud buildups. We get cyclonic flow at 925 and 850. So there's a deep cyclonic flow, which will help deep convection and cloud formation even into the mid portions of the atmosphere. But when it gets to the mid portions and it's also able to build, you still need the winds to be favorable at the upper levels of the atmosphere to be able to push this rainstorm, which is to your east, towards the west or into an area where you are making a forecast for. For instance, we are in Ghana and we are seeing a rainstorm, let's say in Benin or Nigeria or anywhere to our east. And then we see that the winds at the lower levels are okay, they are favorable. So they will sustain the cloud formation. You are seeing deep convergence at 850, and so it will also help these clouds to continue to build. At 700, the winds are easterlies. So we call 700, this is the mid level. We call it the steering level because let's consider a desk. If you are pushing a desk from the mid portion, you are able to move most of the desk along in the direction where you are pushing it towards. But if you are pushing it from either side, whether from one side or the other, you end up pushing that part where you are exerting the pressure on, and then the other parts of the desk will be left behind. And so if you want to move majority of the desk, you either push from all directions or push from the mid portions. And so when a storm is to your east and then the winds at the 700 hectopascal are favorable and pushing them towards your area, they are very strong and can push them faster. Then you get the majority of the storm coming into your country. If the 200 hectopascal, which is the high level, is also in the same direction as the mid level or the 700 hectopascal, then you get the winds moving the storm in the same direction. And so there's a higher probability that the storm will come into your area and affect you. But in the instance or in the case where you are getting 700 hectopascal, moving the direction in the storm in one direction, and then the 200 also moving it in a different direction. What happens is that the tops of the clouds will be shed off by the 200 hectopascal level winds. Why this thing is still messing me up. The top of the clouds will be shed off by the 200 hectopascal level winds. And so you'd want them to be in the same direction to move bulk of the storm towards the area where you are making the forecast for. But if they are in different or opposite directions, then you would expect that it will inhibit the growth or the movement of the storm in a way. But if the 700 is stronger than the 200 and the 200 is in an opposite direction, because the 700 will carry bulk of the storm and is also stronger, you would have majority of the storm coming along the 700 level. But in the case where 200 has stronger wind speeds than the 700 hectopascal, then the tops will be shed faster. And so the clouds don't grow so much. And so they don't produce so much rainfall like when they are all in the same direction. So that's how you use the direction at the high levels to also help you in forecasting. All right. So this is an example of a wind at 925 hectopascal, which is low level wind. All right. So from here, we can see that the winds are moving from the ocean. So the direction is southwesterly as they hit the country. The source is from the ocean because the winds are moving along the coast before they get into the country. And then when they get into the mid portions, they turn there in the anti-clockwise manner. So what it means is that we are getting a trough line or trough axis just around these areas. So cyclonic flow for these areas. These areas will therefore be favorable for some cloud formation and then eventual precipitation. But if we move towards the north, you are seeing that the winds are actually coming from the northern African areas. And so they are mostly easterlies, dry winds coming there. And they are even stronger for the upper regions. And so you would expect more drier conditions to affect the upper regions of the country. But towards the south, you'll be getting some moisture coming in. But because the winds here are not too strong, the moisture that will be coming into the country will also not be too high. So that's what I was saying. You don't just consider the direction. You also are interested in the speed. You are interested in the source of the wind, and you are interested in whether it is cyclonic or anticyclonic flow, whether it is clockwise or anti-clockwise. All these things will affect or influence your forecast. So on a 95 hectopascal level, you are looking out for the anticyclonic vortices and the cyclonic vortices. The winds will be moving from anticyclonic vortices into cyclonic vortices. So if you are getting this anticyclonic vortex over the ocean, pumping moisture into the country, maybe there's a cyclonic vortex somewhere in the country, then you expect more moisture to be thrown into that low vortex or cyclonic vortex that you are seeing within that area. But if the opposite happens, where you're getting winds from the anticyclonic vortex over land, then you are getting them bringing in dry conditions into the cyclonic vortex. So you look at where the vortices are located and the effect of the winds over your area. And this is at 850. At this area too, you are looking at the source of the wind, the speed of the wind, whether there's a cyclonic or anticyclonic vortex or flow, and then whether there's convergence or divergence happening. So, for example, I was talking about streamline convergence and then streamline divergence. So let's consider this wind for instance. So around this area, you can see that from the east, the winds are between around 15 knots. So these ones, they are around 15 knots or about 7.5 or 8 meters per second. But when they get here, they become about 10 knots. So what it means is that there's a streamline convergence just around this area or velocity convergence just around this area. So in a matter of time, the winds will be able to converge at one point. And so if this is coming from a moist source, but in this case, the source is not that moist, and so you don't expect so much to happen within this area. But for this area, where the winds will have to pass over the ocean, pick up some moisture there before they get into the country, that convergence happening here could favor those areas. So on this chart, you could look out for some cloud formation over the southwestern portion, especially around the central and the western regions of the country, to have some cloud formation and then some rainfall. But in the other parts of the country, this is 850. Even if we had moisture, it was dry around these areas, and we're also getting some dry winds at 850. So the dryness is a bit extending into about 1,500 meters into the atmosphere. But if you move towards these areas, it was a bit moist here. There was even some convergence happening around the transition area. But here, we are getting dry winds there. So it means if we get cloud formations, there will be just clouds that are shallow, and so they will not bring so much. But around the west, we are getting the winds passing over the ocean before they get there. And so with that cyclonic flow or convergence there, they will have a higher probability of getting some rainfall. And so if you are even giving rainfall for the mid portions, you give them a reduced probability. The probability will be higher for the western region than the mid portion. So you use this to also tell the probability you should give to a weather phenomenon that you are expecting within an area. And this is 700 hectopascal level. So if the winds are all moving in one direction, like what I was saying, this is telling you if there's a system around these areas. It's telling you how the system will actually be moving, if it's a convective system or just a rain cloud, which may not be convective. It's telling you how it will be moving. And so this will follow the 700 hectopascal if they are very strong. And so if you are making a forecast for areas in Ghana and you are seeing a rainstorm build around this area, you would expect that this 700 hectopascal will be pushing the base of the cloud towards these areas. And then this one will also be pushing them in that direction. And so areas where you would be very confident that there will be rainfall will be around these areas where the 700 will be pushing the system into. But for these areas, you would not expect anything there. For southern Ghana too, you wouldn't be so sure of rainfall occurring within those areas because the 700 hectopascal is not too favorable in that instance. So you're looking at the direction of the 700, the speed, telling you how